Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy news journalist for over 20 years. Every week, we do an episode here on the channel, all your questions, my answers. And recently, of course, a lot of the questions that we've been getting have been about James Webb. And so we thought we would just gather together as much information as we can about James Webb in one place, try to answer a lot of the questions that you're all having so that you can come up with more complicated questions and hit me with those instead. All right, let's get into a rough episode all about James Webb. The origins of James Webb started in the 1990s, and it's the result of this process that the scientific community goes through called the Decadal Survey. All the astronomers get together, they decide what their top priorities are, and what they want to understand turns into telescope designs. And at that time, what astronomers wanted to understand was the most distant parts of the universe, the parts that are most redshifted, as well as this possible new science, the discovery of exoplanets, and a lot of other things where an infrared telescope would be the best way to observe them. And so astronomers proposed this idea called the Next Generation Telescope. And originally, it was going to cost about $1 billion and come out just around the year 2000, in the early 2010 at the latest. Now, of course, over the time as it got completed, the price rose, the timeline rose, and when it actually did launch, it was up to about $10 billion, and it didn't launch until the end of 2021. And the reason why it became so big and so complicated was because there were a lot of very technical challenges, things that had never been done before that needed to be understood and accomplished. And so the first part of this is that they wanted to make a telescope that had a very large mirror, a 6.5 meter mirror. And when you compare that with Hubble, which is about a 2.5 meter mirror, it is about 7 times the surface area as Hubble. And you can't fit a telescope mirror that big inside a standard rocket fairing. And so they proposed building one that could actually fold out in 3. As well, they wanted a way to be able to view in the infrared spectrum at some of the places where you need to have a very cool telescope. And so in order to do that, they proposed this idea of a sun shield, this giant umbrella-like structure that would fold out and block the light coming from the sun. Now, it turned into a very large project. NASA did a partnership with the European Space Agency and the Canadian Space Agency to supply additional instruments on the telescope, as well as the launch to be able to get up into space. And as the development of James Webb continued on, and as the price went up, people were very concerned. Partly, of course, because all of this money was going into this one specific mission, and let's hope it doesn't fail. But also, the budget was supposed to have stopped, and yet it was continuing to go up. And that meant that other missions had to be put on the sidelines, other budgets had to be cut. It's described as the telescope that ate astronomy. And when you think about the cost, $10 billion, like that would have bought multiple Hubble Space Telescopes could have been launched at the same time. And so the question always is like, would astronomers prefer to have James Webb or multiple Hubble Space Telescopes when Hubble Space Telescope is oversubscribed? And it really just came down to the complexity, the technical risk that was taken on as part of the process of developing James Webb. You had this sun shield designed to block the light from the sun, the moon, and the Earth. It had never been tested before. You had this articulating actuators that had to be able to unfold all of the parts of the telescope, hundreds of them. This idea had never been tested before. And so there was many different parts that were really, that science was developed as part of creating James Webb. The segmented mirrors and their ability to align themselves so precisely. The coronagraph on board James Webb that allows it to block the light from a star that it's observing the planets beside of it. So much technical risk went into this one mission, and that's why it took so much longer and why it cost so much more. And then for the next few decades, we watched and waited as James Webb was constructed. It was constructed by Northrop Grumman, and as well as other suppliers The Canadians built their instrument, the Europeans built their instrument, and everything was brought together in the US and assembled and tested and then tested again, and there were problems and it was tested again. And finally, in the end of 2021, the telescope was completed and shipped down to its launch facility at French Guiana. And this is the European Space Agency's launch complex. As part of their contribution to building James Webb, they supplied the launch to be able to carry this into space on an Ariane 5 rocket. In fact, one of the last launches of the Ariane 5 rocket. And for a few years leading up to the launch of James Webb, I gotta say, we were all very nervous. And if you read the kinds of comments that we were having on our YouTube channel, people were very negative. People were very grumpy about how long this telescope was taking. And it was a huge relief that the telescope launched perfectly. The upper stage detached perfectly. It flew towards its final destination at the L2 Lagrange point and didn't seem to be any hitches at all. And in fact, the European Space Agency was able to calculate that the trajectory was so precise that it probably was going to add years to the lifespan of James Webb. James Webb is now at the L2 Earth-Sun Lagrange point. And this is a gravitational balance point where the gravity from the Earth and the Sun, as well as its orbital velocity, balance out perfectly, and the telescope is able to orbit in this one position with a minimal amount of fuel. Now, it's not stable, it's unstable, and so without regular firing of its thrusters every month or so, it will slowly drift out of the L2 point and get away from its current position and eventually no longer be able to function. And the reason it wants to be at L2 is because now that it has deployed its giant sun shield, it can block the light from the sun, the Earth, and the moon, all of which contribute to glare and temperature. And so the telescope can cool down to just a few dozen degrees above absolute zero. And cooled instruments can get very close to absolute zero. And the reason you want the telescope to be cold is because it's viewing in the infrared spectrum. The infrared spectrum is, we feel infrared as heat. We can't see it with our eyes. And so you need to have a telescope that is capable of seeing this heat. But this heat, you might feel the heat coming from a hot stove, but in fact, if you go all the way down to, again, just a few degrees above absolute zero, there's still some heat coming off objects, and this is what an infrared telescope is able to observe. And once you're observing in these wavelengths, there are whole fields of view that are not visible with regular telescopes. There's two main areas for this. One is regions which have been redshifted. So we know that the universe is expanding, and as the universe expands, the wavelengths of light coming from objects that were released billions of years ago, their wavelengths increase. They may have started out in the visible spectrum, but they've expanded out and they've become redder and redder over time. And eventually they've reached the point where they're now in the infrared spectrum. You can't point the Hubble Space Telescope at some of these wavelengths and be able to see anything. You need to have an infrared telescope. The other thing that infrared is really good at is being able to observe through gas and dust that is obscuring your view to some object. Good examples of this are planetary systems, which are forming inside a nebula of gas and dust. Without infrared, you just see the blob of gas and dust, but you can't see the stars and the planets forming inside. Once you can be able to view in infrared, you can actually see the newly forming star, the protoplanetary disks surrounding it. And James Webb is going to be perfectly able to see these kinds of objects. At the time that I'm recording this video, we're about a month away from when we're going to see the first science images of James Webb. And because every part of this mission so far has gone perfectly, every instrument is deployed, it's gotten down to its operating cool temperature, all of the parts have been completed, its focus is right, we're expecting that the first science images are going to be exquisite. They're going to be as expected. But we got a bit of a sneak preview because the telescope was doing its focusing test and it was looking at a region of the sky that had actually been imaged in the past by other infrared observatories. And so you got to see this image first in the WISE telescope, which is several years ago, and then in the Spitzer space telescope, which is one of the best infrared space telescopes out there. And then you got to see the same region in James Webb, and you can see the difference. What starts from blobs of stars to blobs of stars with some kind of background blob, and then with James Webb, you can see the stars have been resolved into points, and you can see the nebulosity surrounding it. And that gives you a sense. But not to mention, faintly in the background, there are other galaxies. And so the amazing thing about James Webb is the longer it stares at any part of the sky, it will be able to resolve deeper and deeper into the universe, revealing fainter and fainter objects. And of course, I'm sure you're familiar with the Hubble Deep Field. This is when the Hubble Space Telescope stared at a previously thought to be empty region of space for hours, days, continuous observing time. And what was thought to be empty space turned out to be filled with tons of galaxies, but it took it a very long time. James Webb can do this wherever it looks fairly quickly. And so it'll be able to produce the equivalent of what Hubble did, but many times over. And it'll be able to do its own version of the deep field. It's going to be able to look right out to be able to see galaxies that are forming just a few 100 million years after the Big Bang itself in any direction that it chooses. So what are we going to be able to see when James Webb starts going into its full science operations? Well, the main big question that astronomers want to ask is, what did the universe look like when it was just beginning to form, when the first galaxies were coming together just a few 100 million years after the Big Bang? Were there fairly large galaxies that all formed at one place, one time? Or did you get these smaller dwarf galaxies that formed individually and then came together, merged into larger and larger objects, and eventually we get the large grand spiral galaxies that we'll see today? James Webb, because of its ability to see this red-shifted light, to see these first galaxies, should be able to see these building blocks coming together and answer these fundamental questions about the nature of the large-scale structure of the universe. But Webb will also be able to operate much closer to home. James Webb is going to be able to peer through the gas and dust at the center of the Milky Way and be able to see the region around the supermassive black hole at the heart of our galaxy. It's going to be able to see stars whipping around this supermassive black hole as if they're comets going around the sun. It's going to be able to see through the obscuring gas of the Milky Way and better chart the galaxies that are on the other side. People always ask this question, what is the great attractor? It's going to be able to see the galaxies at where they're moving towards and help map out the shape of the great attractor. People always ask if it's going to be able to see a view of the actual supermassive black hole, and the answer is no. The Event Horizon Telescope was a telescope the size of planet Earth. Well, James Webb is just one instrument, 6.5 meters across. It's not going to be able to the same amount of resolution, but it will be able to see the region around the supermassive black hole with a level of clarity that we've never seen before. James Webb will be able to see exoplanets. And not just like detect exoplanets, although it will be great for doing that, but it will actually be able to directly observe them in very special cases. And those cases are when you've got an Earth-sized planet orbiting around a red dwarf star. The reason is because the star is putting off a tremendous amount of illumination. It could be like 1 million times more illumination than the planet that's orbiting around it. James Webb has a coronagraph on board. This is a gadget that is designed to block the light from the star, revealing the light of the planet beside it. But it can only work when the brightness is this factor of about 1 million or so. When you compare, if you wanted to say see another Earth compared to the sun, it would be like 1 billion times brighter. So James Webb isn't going to be able to do that yet. But once it's able to observe these planets, it's going to be able to sample the chemicals in their atmosphere. It could detect the presence of water vapor, oxygen, ozone, carbon dioxide, methane, other things like that. It'll give us some kind of hint about the conditions on these planets, their weather, their cloud formation, and maybe, just maybe, some sense that there could be life there. Although biosignatures, this idea of searching for life, is going to be very tricky. It's even been estimated that if it made observations of the planet around the nearest star system to us at Proxima Centauri b, if there was an advanced civilization creating pollution in their atmosphere like chlorofluorocarbons, James Webb might be able to detect it. So it's a very powerful tool for being able to image and examine planets. And of course, it's going to be able to observe objects here in our solar system as well. There are many objects in the outer solar system which are cool. Asteroids, Kuiper Belt objects, objects coming out of the Oort cloud, comets, the moons of various planets. It might be able to make observations of Planet 9 once that's found. So James Webb will have a role to view objects here in the solar system as well. People always ask me what I'm most excited about. And I mean, obviously I want to see the beginning of the universe and I want to see to the heart of the Milky Way, but I really want to see planets. And one of the most exciting places that we can see is the TRAPPIST-1 system. This is this red dwarf star that seems to have half dozen Earth-sized planets orbiting around it. Some too close to the star, others in the habitable zone, and others are farther out. And like, imagine that we will get images of each of these planets that can then be studied to figure out what their atmospheres are like, what their day length is like, what their weather conditions are, maybe get a sense if there's life there. It's really exciting. And I think if there's one science result that I'm most looking forward to, it's going to be the first images from TRAPPIST-1. Over the coming years, astronomers will submit proposals to the Space Science Telescope Institute. These are the same people that handle the observations made by the Hubble Space Telescope. And what's really cool about James Webb and Hubble is that the telescopes are freely available to anyone in the world who can make the science case to the steering committee. And they can come from any university, any researchers, anybody who can make the case can get free time on the Hubble Space Telescope or James Webb. They don't have to pay for it. The data is published to the internet, and the archive for James Webb will grow and grow and grow. And so if anyone wants to be able to look through this data, they can. If they want to study it and analyze it for themselves, they'll be able to do it. People have been asking me, what are the images going to look like? Because the first images that we've seen so far look like this weird orange blob. And that's not what the pictures are going to look like. These are just images taken in one wavelength of infrared, and you get this one color. But as with the Hubble Space Telescope, James Webb is equipped with dozens of filters that allow it to take images at many different wavelengths. And then those images can be combined to make full color images, the kind of thing that you're familiar with. When you think about the pillars of creation or the deep field or images of the planets by Hubble, you're looking at an image that was taken with multiple wavelengths, different filters, which were then combined to create a full color image. And the same thing will be possible with James Webb. And so if you want to get a sense of what images from Webb are going to look like, look at the images that came back from Spitzer. That's another infrared telescope. Or maybe Herschel, again, in the infrared, but multiple wavelengths of infrared combined to create these just absolutely stunning pictures that are both as artistically exciting as they are scientifically exciting. I'm sure you're wondering how long James Webb is going to last, and its original expected lifetime is about 10 years, which I'm sure you're wondering. I mean, that's fairly surprising compared to Hubble has been in orbit now for 30 plus years and is going and going. And the reason is because Webb is far away from the Earth. It can't be serviced. It can only last in its orbit as long as it has propellant on board to maintain its position at the L2 Lagrange point. Once it runs out of propellant, it will drift away and it will no longer be able to do its job. It also has a lifetime of coolant on board that's going to allow it to keep its most sensitive instruments just a few degrees above absolute zero. But according to engineers, the launch that carried Webb to its final position was so precise that it didn't need to use almost any of its onboard propellant to maintain its current position. And so it's thought that that may extend its time period out another, say, 5 years. So it could last about 15 years, maybe a little longer. And although there are no plans in the works to extend the lifetime of the system, to maintain it, to refuel it, any of that, it is theoretically possible. When Webb was launched on top of its upper stage rocket, it had a fuel connection and a docking clamp that was attached to the upper stage. And so it still has these. And so you can imagine in the future, some starship could fly out with a bunch of astronauts. They could clamp on to Webb's docking ring, refuel it, maintain any of its instruments, and allow it to keep going for a lot longer. So although right now there are no concrete plans to have the mission last longer than its expected lifetime, I would be surprised if someone didn't consider a way to try and recover it near the end of its lifetime. Now, this is just the tip of the iceberg of the information that we've got here on our channel about James Webb. If you want more information, I've got an hour-long interview with Dr. John Mather, Nobel laureate, the person who came up with the idea of the James Webb Space Telescope. And we talk in detail about how the idea came together and the kinds of science questions that he was hoping Webb will answer. I've also talked to Dr. Klaus Pompopoutin. He works on the team who's designing the targets for James Webb. And so we spend about an hour again talking about the kinds of targets that astronomers have been requesting for Webb and what we can expect it to be observing over the first year at least and into the next couple of years. So if you want more information behind the scenes, we've got it for you here. And these are just a fraction of the interviews that I've done here on the channel. I've talked to hundreds of space scientists, astronauts, astronomers, engineers about the missions they're working on. So if you really want to dig deep and understand where we are in our understanding of the universe, space exploration, you're going to want to dig into the interviews. They're fascinating. All right, well, that's an overview of where we stand with James Webb right now. And I'm sure this has generated a ton of new questions for you. So go ahead, put them into the comments. I'll try and gather a bunch of them and include them in our question show that we record every Monday. And of course, the second we see the first scientific image coming from James Webb, I will absolutely let you know, and we will probably do a show about that too. I hope you enjoyed this. If you want more information about space and astronomy, subscribe to this channel. You'll get our question shows, you'll get our news shows, our interviews, and lots more information to answer any of the questions that you might have about space and astronomy. Thanks for watching, and we'll see you next time.